Santa Barbara, and then he moved to Harvard as a junior fellow before he moved to UC Santa Barbara as a professor. Cenke is an expert on quantum field theory applications in strongly correlated system, logical phase of matter, and quantum information. Today, he will talk about topology and quantum criticality under weak measurement and decoherence.
Yeah, thank you. So I want to thank EG for the invitation. And well, I was in Boston area as a postdoc for 3 years, but I don't think I ever been to this campus before. So this is my first time visiting Northeastern University. So I will share some of our recent work on quantum criticality and topology under weak merriment and decoherence. So I will certainly explain what weak merriment and decoherence means. So let me first acknowledge my collaborators. Oh, it seems like there's a problem going down. Okay, my collaborators. So basically, well, I mean, I learned a lot, about quantum information from the younger generation of physicists, including John Lee, who was a KITP postdoc, but now actually he's a faculty member in UIUC. And also learned from Yizhuang You, who is actually a faculty member at UCSD, and Chao Ming from Cornell. And actually my collaborators also include Cheng Wang from Perimeter Institute, and my students, Na Yang and Kai Xiang from Santa Barbara. So yeah, so here's the plan. So I will try to first introduce the notion of weak merriment and decoherence. And also I will really emphasize two different kind of symmetry conditions. So basically so most of the talk I will try to use quantum field theory techniques to describe quantum information problems. So I mean, as you probably know, that in quantum field theory, to getting the symmetry right is actually the most important step. You definitely need to get the symmetry right to write down the Lagrangian, to run RG, and many things that we do in quantum field theory will rely on the symmetry. So I will try to emphasize that there are two kinds of symmetry conditions. Two possible symmetry conditions in this kind of quantum information problem. And then I'm going to develop a formalism, which I will apply to the quantum critical points and also topological states of matter under decoherence. Okay, so these are the references in this slide. Yeah, so let me first introduce what is decoherence. So basically, decoherence is actually the link between the quantum state and a classical state. So basically, actually, in the decoherence process, the quantum state will gradually lose their quantum coherence and become a mixed state, more classically. So let me give you just an example. It's the simplest quantum state ever. It's just a spin up plus spin down state. And it's actually, we can also view this as a state with the spin pointing to the right. It's the simplest quantum system ever with just one qubit. So basically, the rho, which is a 1/2 2x2 identity matrix plus the sigma x, is the density matrix for this state, and it's a pure state density matrix. We know it's a pure state density matrix because a trace rho equals to 1, and also trace rho square is also equals to 1. Okay, so it's a pure state density matrix. Okay, so this is how the decoherence works. So the rho d on the right-hand side, you can see the first term of rho d means that, so the first term of rho d is just a pure number times the rho. So this means that actually when the qubit goes through a cloud of ancillary spins or cloud of environmental spins, okay, there's a big probability for the density matrix to not feel anything at all. It means that actually there's a probability for the density matrix to not entangle with the environment at all. So that means the density matrix will actually come out the same density matrix with a big probability 1 minus 2p. But there's also a small probability p for the state to be measured along the z direction and get outcome z equals to 1. Okay, so if I get z equals to 1 outcome, then the density matrix will become 1 plus z over 2, okay, with the probability p. And suppose there's no post-selection of the outcome, then of course we should get another outcome, which is z equal to -1 with the equal probability p, okay? So basically the outcome, the decoherent density matrix, we have 3 terms here. And if we just group them together, it takes the form on the second line, okay, take the form on the second line. Basically, it's the original form times a bigger probability plus another form, z rho z, okay, times a small probability p. Okay, so at this very, very early stage, we can already emphasize there are two kinds of symmetries here, which is at play here. So for example, the original state psi is obviously invariant under the action of operator x. Okay, you can use x operator on it, it's going to be invariant. Okay, so then the density matrix rho, you can check you can check, it's very easy to check. The rho will have a double symmetry because I can use x to operate the rho from the left and operate the rho from the right. Okay, separately. Okay, so rho is invariant on the separate operation of the x from the left and the right. So it's double symmetry. So for a pure quantum state, which is invariant under certain symmetry, okay, so once we write it in a density matrix form, at least very naively, it looks like there's a double symmetry. Okay, double symmetry, or we can call it a strong symmetry condition. Okay, but now let's look at the final decoherent density matrix. Okay, you can immediately tell this density matrix on the second line is not going to be invariant under separate operation of the x from the left and right. Okay, because actually, if you operate x from the left, it's going to anti-commute with the z operator. Okay, it's going to change the form of the decoherent density matrix. Okay, so it's not going to be invariant under the separate and left and right operation of x. However, it's still going to be invariant under the simultaneous action of x from the left and right. Okay, because the z will anti-commute with x, give it a minus sign, and give it a minus sign again from the right. Okay, so that means that the decoherent density matrix will actually have a diagonal symmetry. Okay, we have a diagonal symmetry. Okay, so why is that? Okay, why is that? So it turns out that there's a simple explanation for why the symmetry is broken from a double symmetry to a diagonal symmetry. Okay, so when the ancillar space is mirroring the single space, the target system. Okay, so every measurement breaks the Z2 symmetry. Okay, every measurement breaks the Z2 symmetry. It breaks the Z, either Z equals 1 or minus 1. But eventually, we sum over all the measurement outcomes without any bias. Okay, is that right? So because we sum over all the measurement outcomes without any bias, then eventually the density matrix will have a diagonal symmetry. Okay, we have diagonal symmetry. So yeah, so this is a simple illustration of the double and diagonal symmetry, which will play an important role for the later part of the talk. Okay, so it turns out that this kind of a diagonal and the double symmetry actually they are certainly they can be true for a quantum many-body system. Okay, so we know that actually for very complicated quantum many-body system, usually we don't even know the exact Hamiltonian of the system, but we can still say things about a symmetry. Okay, we can still say things about symmetry. So let's say that I have a system with the Ising symmetry, for example. It's a quantum many-body wave function with the Ising symmetry. Just like the previous simple case, the density matrix for this pure state will have double symmetry. Okay, so now let's say that the quantum many-body system goes through this ancillar space, cloud of ancillar space. Okay, and what happens next? So it turns out that suppose the ancillar spins in the cloud only measures like the energy density or particle numbers. Okay, these quantities which are invariant under the Z2 symmetry. Okay, if the ancillar spins only measure quantities invariant under the Z2 symmetry, then the outcome, the decoherent density matrix, will still have the double symmetry. Okay, see what I'm saying? We'll still have a double symmetry because every measurement does not break this Z2 symmetry at all. Okay, so it means that even though I get a decoherent and mixed density matrix, it still have a double symmetry. Okay, or strong symmetry. But suppose the environment measures, okay, the Ising spin or the Ising order parameter in any sense, and eventually we sum over all the measurement outcomes equally without any bias, then I will get a diagonal symmetry condition. Okay, I get a diagonal symmetry condition. So this kind of symmetry conditions works actually in quantum many-body system as well. Okay, so this is the picture number one, but there's also a more condensed matter version of picture number two of how to understand these two symmetry conditions. Okay, this actually is a more condensed matter case. So for example, when I say the system is being measured by the ancillar spins, what I really mean in a full quantum mechanical sense is that the system, my system, and the environment, they are governed by one Hamiltonian, one big Hamiltonian, okay, with an interaction between my target system and the environment. Okay, for example, the term here. Okay, sum over a bunch of operators, and this is the OS, is the operator in the system, and this OA is the operator of the ancillary space. Okay, so let's say that my system has a symmetry U1. Okay, let's take U1 as a symmetry. This is the more familiar condensed matter example. Okay, if I have a U1 symmetry and my target system originally is the eigenstate of the U1 symmetry, which means they have a fixed particle number. Okay, so it has a fixed particle number. Okay, then suppose these two operators here, OS and OA, they are both singlet on the U1. Okay, which means OS, for example, here is like energy density, and this is some other operator which is invariant on the U1. Okay, then this interaction will actually evolve my pure density matrix into a mixed density matrix, but it does not change the particle number at all. Okay, so every eigenstate of the decoherent mixed density matrix will still have precisely the same eigenvalue of the U1 charge as the original pure state I start with. Okay, or in other words, in this case, this density matrix is evolving in the canonical ensemble. Okay, in the canonical ensemble. Okay, it does not change the particle number at all. It has fixed particle number. But in the second case, okay, suppose the interaction term preserves the U1 symmetry. However, it preserves in the way that I allow my particle to hop in and out from my system to the environment. For example, this is the B diagram in B. Okay, I allow the particle to hop in and out from the system. Then after tracing out the environment, I will get a density matrix, which is the mixed ensemble of different particle numbers. So every eigenstate of the mixed density matrix will still be an eigenstate of the U1 symmetry, but actually every eigenstate may not have the same particle number anymore. Okay, this is a diagonal symmetry. Okay, and actually in condensed matter we call it the grand canonical ensemble. Okay, the rho involves in grand canonical ensemble. Okay, so so this is the two symmetry conditions which I would like to emphasize. And also let me emphasize that in this talk, I will try to focus on the scenario where the P is actually small. Okay, P is small. It means that actually the system is only being weakly measured by the environment. Or in other words, I evolve the system with the environment under this interaction by a short amount of time. Okay, by the amount of time which is small compared with the 1 over h, for example, 1 over h. Okay, but let me clarify that this scenario I assume, which means that there's a weak mixture of weak entanglement between the system and the environment. This actually is not that relevant to ordinary condensed matter system, because in ordinary condensed matter system, turns out that the time scale is very short. It means if I expose my condensed matter system to the environment, even for a short amount of time, it's going to be fully thermalized because the time scale in the ordinary condensed matter system is actually very short. Okay, so by the time we do measurement on condensed matter system, the system is already being strongly measured. Okay, strongly measured or strongly decohered with the environment. Okay, but this procedure, this assumption I made may be relevant. Actually, can be very relevant to many other systems, like the quantum computer platform, many quantum computer platform, quantum processor platform, like trapped ions or like the superconducting circuit or something like that. Because in those systems, the decoherence time can be long, and they can do measurement or manipulation far shorter, okay, than the time scale. So it means that this scenario is more relevant to those systems. Okay. Yeah. Okay. So here's a little bit of math here. Okay. Here's a little bit of math. So for a complicated quantum many-part system, okay, normally we don't really know the ground state wave function. Okay, we don't really know the ground state wave function. Okay, but we know how to do approximation, how to get approximate wave function in condensed matter. We have developed this formula. Okay, so normally this is what we do. Okay, so we have in order to compute a density matrix, suppose I want to compute the rho naught, which is the original ground state pure density matrix. And it's a matrix element sandwiched between phi 1 and phi 2. So phi 1, let's say phi 1 is a configuration of Ising spin. Okay, and phi 2 is another configuration of Ising spin. So the rho naught should be a matrix element, okay, between the phi 1 configuration and the phi 2 configuration. So how do we compute this? Okay, so there's a well-defined field theory technique to do that. Okay, so to compute this, basically we have to perform a path integral. Okay, perform a path integral with a action S Okay, so the action S can be derived from the Hamiltonian. It can be derived from the Hamiltonian. And actually we fix the imaginary time tau equals 0, the phi configuration equal to phi 1, and fix imaginary time tau equals beta configuration equal to phi 2. Okay, so let's imagine that we can do the path integral. Okay, normally we cannot do it precisely, but suppose we can. Okay, then after taking beta to infinity, this will give you the matrix element. Okay, this will give you the ground state matrix element, or the ground state density matrix element between phi 1 and phi 2. Okay, and even though most of the time we cannot do this exactly, we can. There's a lot of approximation method developing condensed matter over the last half century or even longer. Okay, so we can approximately calculate the path integral in the saddle point and many ways. Okay. Okay, so what about under decoherence? Okay, so let's just recall what we did here in the first example. Okay, so basically there's a big term which does not change the form of rho, and then there's a second term, a smaller term, with an operator operating from the left and an operator operating from the right of the rho. Okay, so in general that's also true. Okay, in general it's true. So under decoherence, the density matrix will just be a sum over a bunch of k operator operating from the left times k operator operating from the right. Okay, these are called Krauss operators. Okay, these are called Krauss operators. And let's imagine the first big Krauss operator is just identity. Okay, it just there's a big probability for the system to not feel any merriment at all. Okay, so there's a rho plus a bunch of perturbations. Okay, those perturbations always take the form of some operator operated from the left and some operator operated from the right. Okay, and the operator operating from the left is like operating something at imaginary time tau equals to 0. Okay, the operator operating from the right is like operating something on time equals to beta. Okay, so eventually I can encapsulate this form into an extra term in the action. Okay, S interaction, another extra term in the action. And this action will only involve field or configuration at tau equals 0 and tau equals beta. Okay, so that means that actually to compute the decoherent density matrix, all I need to do is to do a new path integral. Okay, do a new path integral with the old action S plus the extra term here. And this extra term actually will have a tau, will have phi tau equals 0 and a phi tau equals beta. Okay, and then how do we determine the form of this this extra term? It's a symmetry. Okay, a symmetry will determine the form of this of the action. And actually, you know, so if you have learned a normalization group and many things like that, you understand that actually the exact form of this extra term may not matter so much, because eventually, okay, they flow to a fixed point. So what happens? What's important is what happens as the fixed point. Okay, so here's the logic, right? The symmetry of the decoherence channel will determine the form of the extra term in the path integral, and actually will determine the fixed point. And that fixed point is actually what we are interested in. Okay, so here, so now I have mapped a quantum information problem to a field theory problem. And for field theory problem, the advantage is that we don't really have to worry about the microscopic details. It's the IR fixed point that we are worried about. Okay. So you can also see that because the decoherence problem is now mapped to the problem which happens as the temporal boundary, okay, tau equals 0 and tau equals beta, okay? So it means that I have mapped the quantum information problem to the problem as a temporal boundary. And in many systems, there's a Lorentz invariance, okay? There's an emergent Lorentz invariance, okay? So actually we can do a space-time rotation and map this into a problem concerning the spatial boundary, okay? Then you can see that, okay, suppose I want to reverse engineer. Okay, suppose I want to reverse engineer the problem. Okay, I want to ask, what kind of system can have interesting physics under decoherence or weak merriment? Then this question is equivalent to what kind of system can have interesting boundary physics? Okay, can have interesting boundary physics. Then the answer should be very obvious, because first of all, topological states can have an interesting boundary physics, right? So topological states probably have interesting physics under decoherence. Okay, another interesting, another scenario is the quantum criticality, where quantum critical points also have interesting boundary physics, which is less well known, but still, they have non-trivial boundary physics to explore. Okay, so basically, this talk I will try to go through. Okay, I will try to explain our investigation of the two kind of states. One is the quantum critical points, like the Wilson-Fisher fixed points under decoherence. Okay, the problem is going to map to the boundary critical point, sorry, boundary critical field theory. Another problem is actually the chain insulator and other symmetry project topological states under decoherence. The problem will be mapped to how do we handle the boundaries of these states. Okay, so it turns out that both systems can be interesting on the decoherence. Question?
And in general, your interaction action, which is reaching into this boundary physics, are they like the two boundaries are coupled? Like they have
Yes.
local terms and
Yeah, in general, they are local if the decoherence is local. So, for example, the ancillary spin here only mirrors the neighborhood of it. It does not mirror the entire system. So the interaction will be local if the decoherence channel is local. Yeah, that's right. Yeah, right. So and also actually we have to assume that it's a weak decoherence or weak merriment. Although some of the results actually can be extended to stronger decoherence. I can mention examples like that later. But actually, the formalism, I'm most comfortable with the formalism actually when we talk about weak merriment and weak decoherence. Okay. Question?
Just at the very beginning, just to check my understanding, the decomposition of the density matrix there's some large probability that there's that it doesn't decohere at all. That assumption is only reasonable if your interaction term is weakly interacting. So it's like you wouldn't be able to
Actually, as long as even if it's strong, as long as I evolve with a short amount of time, the time is actually shorter than 1 over h. Well, actually, it's more like h bar over some energy scale decided by the interaction scale. As long as the time scale shorter than that, so that right. Then I can make this assumption.
Right.
Yeah.
You can say that.
Yeah. Okay. So let's first look at quantum critical points on the decoherence. So let me first say that actually this similar formalism was first developed in the following paper in the Berkeley group. They tried to analyze the 1 + 1 dimensional Lattinder liquid under decoherence and weak merriment, and actually they used some well-known result developed by Matthew Fisher and Charlie Ken in the 90s about the defect and the boundary of the 1 + 1 dimensional Lattinder liquid. So let me focus on the 2 + 1 dimensional quantum critical points, which I think the physics actually are a lot more interesting, and some of the boundary physics of 2 + 1D quantum critical points were only understood in very recent years. Okay, it's a new problem rather than an old problem. Okay, so right. So just to review the basic formalism, we want to understand. So let's say that I first prepare a quantum ground state. Okay, the quantum ground state is a ON Wilson-Fisher critical point. Okay, so I tune a 2 + 1 dimensional system to a critical point with the ON symmetry, and this fixed point is the ON Wilson-Fisher fixed point. And then I take this wave function and then let it expose to the environment, okay, for a short amount of time. Then I take out the mixed density matrix and I investigate what happens. So based on the formalism I developed before, this boils down to compute this path integral with extra term, okay, extra term, which actually couples the tau = 0 boundary and tau = beta boundary. Okay. So to understand this, so let me first try to review some basics about the boundary of a critical point. Okay, boundary of a critical point. Okay. So this actually is a very old subject. Okay, this is a very old subject. So suppose I look at a capital D dimensional classical critical point. Okay, and D can be large. Okay, let's say D is very large. A capital D dimensional critical point in classical space. And I want to look at the boundary. Okay, look at the D - 1 dimensional boundary. Okay, so what happens? So naturally, the bulk theory is correspond to a phi-4 theory. Okay, it's like a Landau theory, like a phi square plus phi 4. Okay, this kind of action. Okay, this kind of free energy expression. So obviously there are two tuning parameters. One is the phi square term R in the bulk. The other is the phi square term as the boundary. Okay, and actually we want to look at R equals 0 line. Okay, the horizontal line with R equals 0. So it means that I want to fix the bulk to be as the critical point. Okay, but then the boundary epsilon, the mass term as the boundary, can still be either positive or negative. Suppose the boundary term is positive, it means that the boundary does not want to order. Okay, is that right? The boundary does not like order. If epsilon is negative, then the boundary wants to order. Okay, boundary wants to order. So in the boundary criticality literature, which actually is a very popular field in the early 80s. Okay, the early 80s. I know that this is way before any of you were born, but still, in the early 80s, well, it's also around the time I was born, but in the early 80s, basically this side is called ordinary boundary condition. And this side is called extraordinary boundary condition. Okay, extraordinary boundary condition. So basically this side is understood pretty well in the 1980s. Okay, the ordinary boundary condition. So basically when epsilon is positive, okay, when epsilon is positive, what happens that the boundary has a mass term. So you may think, okay, the boundary has a mass term. If I measure the phi correlation function, it's going to decay exponentially. Okay, but that's not quite the case because actually the bulk is actually critical. Okay, the bulk is critical. So it turns out that in this case, what happens is that if you measure the phi correlation near the boundary, you will still see a power law correlation, but the power is going to be much bigger than the bulk. Okay, much bigger than the bulk. So for example, this is the right. So this is the bulk critical point. Sorry, this is the bulk scaling dimension, and this is the boundary scaling dimension. Okay, it's actually differ by 1. Okay, pretty much 1. Okay, but of course, there's an epsilon, correction. But let's say that it's pretty much increased by 1. Okay, intuitively, this actually makes sense because the boundary has extra mass terms that does not want to order. Okay, does not want to order. But now the question happens. So the question is that what happens when epsilon is negative? Okay, when epsilon negative, it means that the boundary wants to order. It may even wants to order before the bulk. Okay, so that means that it seems like it's possible for the boundary to order first and the bulk order next. Okay, but then immediately realize this is a problem when d equals to 3, when capital D equals to 3 with the ON symmetry. Okay, because suppose the bulk D is a 3-dimension, the boundary is 2-dimension, and we know very well the ON symmetry cannot order at a 2-dimension. Okay, ON symmetry cannot order at all at 2-dimension. Yeah, but still there's an issue because the bulk is critical. So the boundary is not really a local system. Okay, the Mermin-Wagner theorem doesn't really say much about the non-local system for ON symmetry. So what's going to happen? Okay, so what's going to happen? So it turns out that this was only understood, precisely 3 years ago. Okay, by Max from MIT. Okay, so he actually started the problem. He really take a classical 3D Wilson-Fisher fixed point and studied the boundary. So the answer he found was that when epsilon is negative, turns out that actually this extraordinary phase still exists, but actually it's should be renamed extraordinary log. Okay, so what this means is that when epsilon is negative, if I measure the phi correlation near the boundary, I'm going to get something almost long range order, but not quite. Okay, you can see that it's 1 over log x to some power. Okay, it means it decays, but decays extremely slow. Okay, decays extremely slow. So this is renamed as extraordinary log. So in the early 80s, obviously this cannot be seen because the 1 over log x decay is going to be very, very, very slow decay, and the computers back then actually probably would not be able to see this at all. But today this has been seen. Okay, so after the prediction, it has been seen numerically because today we can simulate a much bigger system size. They did see this extraordinary log decay. Okay, so let's come back to our problem. Okay, let's come back to our problem. So as I said before, we are trying to evaluate this matrix and with the extra term. Okay, with the extra term, but actually the correlation function. Okay, when we calculate the correlation function, we want to calculate a trace rho something. Right? When we take a trace of this matrix, we have to glue the 2 temporal boundaries together. we glue tau equals 0 together with tau equals beta. Okay, so it's like I'm gluing this, but then there's a defect. Okay, it means that the decoherence will become a defect. Okay, will become a defect in this 2+1 dimensional path integral. The decoherence will become a 2+0 dimensional defect inserted in this 2+1 dimensional path integral. Okay, and then there is a defect action. Okay, and in this particular example, the double symmetry and diagonal symmetry does not really matter that much. Okay, the reason is that because, for example, this is an action with a diagonal symmetry. Okay, because I have a phi tau equals 0 dot phi tau equals beta. It means that this actually is only invariant on the simultaneous rotation between tau equals 0 and tau equals beta. It is not invariant under separate rotation of tau equals 0 tau equals beta. Okay, but still, if I take a trace, okay, this term becomes just a modified square. Okay, become modified square. So it means okay. So it means actually now the problem becomes, okay, I'm trying to evaluate the correlation function as the defect with the extra defect term, but the bulk is still tuned to be critical. Okay, still tuned to be critical. So it turns out that this was also studied, and actually the result is still the same as before. Result is still the same at the boundary criticality. So depending on the extra mass term as the defect, okay, depending on the extra mass term as the defect, we either get the ordinary defect condition or the extraordinary log defect condition. Okay, extraordinary log defect condition. Okay, so this means that suppose I take a Wilson-Fisher 2+1 dimensional Wilson-Fisher wave function and go through this kind of weak decoherence channel. Okay, maybe followed by a little bit of post-selection. Okay, then actually I take out the mixed density matrix. I start mirroring the correlation function. I should either see this or that. Okay, the prediction is that I should either see this behavior or that behavior. Okay, I'm not supposed to see Wilson-Fisher anymore. So that means the Wilson-Fisher fixed point will be kind of destroyed by even weak decoherence or weak merriment. However, it's not destroyed too much. Okay, we can still predict what's the example, what's the consequence going to be. Okay, the correlation will be either this or that. Okay. Okay, so this is the first prediction that we can make about the Wilson-Fisher fixed point on the decoherence. Okay, so but this is just this is the ordinary correlation question.
So here you just measure the single mixed state density matrix operator on a single density matrix, not on something like the type 2 strange correlator.
No, this is not strange correlator. Yeah.
It's because local quantum channel is equivalent to adding from non-entangled qubits and have local unitary operators acting on that. So does that mean I can have such kind of logarithmic long-range order by adding additional layer to the Wilson-Fisher point and do some local operations and move x?
Yes, right. Yeah, but you need some weak post-selection. Yeah, you need a weak post-selection to get this. Yeah. So right. Yeah. So this is a simple prediction, but it shows you the power of field theory in this kind of problem. Okay. So it's actually I didn't really assume any microscopic details of the decoherence channel at all. Okay, just symmetry alone will to give you the two possible outcomes. Okay. Okay, but let's not stop here. Okay, so let's say that I want to compute something else. Okay, so let's say I want to compute this quantity. Okay, it's a log trace rho square. This is called a Renyi entropy. Okay, and the second Renyi entropy. And actually, again, this boils down to calculating this path integral. But now it's a rho square. It means that I doubled the density matrix. Okay, so it means that tau equals 0 is here. And actually, this is the one density matrix, but I glue it with another density matrix. Okay, and then I turn on interaction between this defect and this defect. Okay, so now this is a new problem. Okay, this is a problem which actually we don't really see in the boundary criticality, because it's like I'm performing the path integral in the 2+1 space-time, but I turn on some interaction between some very non-local interaction between two defects. Okay, we need to compute this. Okay, we need to compute this. So this actually is also doable for a large classical problem, but let me maybe show you one example. So for example, suppose I start with so let me just give you one one result of the calculation. So for example, suppose I start with a system with a double Z2 symmetry. Okay, double the Z2. So it means that there's a Z2 symmetry here, there's Z2 symmetry here, and the interaction preserve the double the Z2 symmetry. So then actually we can show that it's possible for the interaction to spontaneously break the double the Z2 symmetry to a diagonal Z2 symmetry. Okay, it's possible to do that. Okay, so because it's like that. So I have like an IC model here, another IC model here, and the interaction, the decoherence terminal interaction between the two IC model and the spontaneous break the two IC symmetry to a diagonal IC symmetry. Okay, so this can be shown in the field theory and also can be shown with the exact lattice model calculation. Okay, the lattice model model calculation. So this is the calculation done by Zhang Yang and Chao Ming in the paper below. So basically what they did was that they take a Z2 paramagnet and a terminal decoherence. Okay, so what they show was that when we calculate the second Rayleigh entropy, okay, because we doubled the system, okay, because we doubled the system. So the calculation can be mapped to a calculation in a doubled Hilbert space. Remember, actually, for every this matrix, I can take a transpose on the right side and make a double Hilbert, make it a quantum state in a double Hilbert space. So it turns out that the calculation for the second Rayleigh entropy can be mapped to a calculation in a double Hilbert space. And actually, the phase transition I was mentioning correspond to I take an Ising spin here, an Ising spin on the second layer, and they pair and they condense. Okay, they pair up and they condense. So this is the spontaneous breaking of a doubled Z2 symmetry to a diagonal Z2 symmetry. Okay, so it turns out that this phase transition has an information transition dual in a toric code. We know that a Z2 disordered phase is dual to a deconfined phase of toric code model. Okay, this transition has a meaning of that if I take a toric code model and I measure the kinetic energy of the E anion, for example, I weakly measure the kinetic energy of the E anion, then actually in the double Hilbert space, I'm going to cause a pair condensate between the E anion in the top layer and the E anion of the second layer. Okay, pair condensate. So it's like I'm going to break the two Z2 gauge symmetry down to one Z2 gauge symmetry. Okay, and this is the information transition. Okay, this is the information transition. Okay, in the sense that actually the quantum information stored in toric code will be undecodable beyond the decoherence. Okay, beyond the decoherence. Okay, so this transition can be shown in both field theory calculation and also lattice model. Okay, and this P is actually not very small, actually. So it means that the perturbative calculation used in field theory can be right even when P is actually not exactly small. Okay, yeah, because actually we know that many fixed point that we found by doing perturbative RG calculation, it turns out to be correct. Okay, even when the fixed point is not that weakly coupled. Okay, even though the fixed point is not that weakly coupled. Okay, so this is the end of the first part. So any questions so far about the critical point on the decoherence? So next I'm going to move on to topological states on the decoherence. Okay.
So when you talk about that diagonal symmetry,
yeah,
the recent proposal for average symmetry for factor.
Yes, it is. It is. So the average symmetry is actually a symmetry of disorder system. It's a symmetry broken by every disorder realization, but actually on average it's symmetric. They are related. Indeed, they are related. But there's also an important difference which I would like to emphasize here. So basically, in that setup, in every disorder average, so for every disorder average, you will have a state. So it's a density matrix. It's an ensemble. But every eigenstate of that density matrix will be a ground state of a local Hamiltonian. Okay, because every disorder realization is local. But in our case, we cannot guarantee that. Because on the decoherence, I have a mixed density matrix. There's no guarantee that every eigenstate actually will be the ground state of a local Hamiltonian. Yeah. So this difference, this is an important difference. But actually, how important this difference is in terms of classifying states, I think that's still under study. We haven't really understood how much the difference will affect the classification. Yeah. Right. Okay. So now let's move on to topological states on a decoherence. Okay. So let me first introduce a new notion in the quantum information physics, okay, which is well, this is the first Z. Okay, the Z is a trace of one density matrix times another density matrix. Okay, so the first density matrix is the density matrix that we want to diagnose. Okay, we want to study. So target density matrix. We want to study. And the second density matrix is a trivial density matrix, which means that it's a trivial insulator or the trivial disorder state density matrix. Okay, so the first density matrix could be a decoherent topological state density matrix, and the second density matrix is always a pure trivial insulator density matrix. And this Z is called fidelity. We call it fidelity. Basically, just means that how similar these two density matrices are. Okay, just tell you how similar they are. Okay. Okay, and the second quantity F, just take a log of Z. Okay, so normally actually people don't use Z and F because they are introduced in different contexts. But here I use Z and F because actually later I'm going to map Z to a partition function, and F is mapped to a free energy, okay, of something. Okay, so F actually in quantum information is called a second relative radiant entropy. Okay, but here let's just call it it's a free energy of something. Okay, what is this something that we are talking about? So now, first of all, let's take a pure density matrix of chain insulator and a pure density matrix of a trivial insulator. Okay, so basically, if I take a trace, it means that I evolve the system in the imaginary time with the Hamiltonian of a chain insulator in the lower half of the time. Okay, and the top half is evolved with a trivial insulator Hamiltonian. Okay, then this trace corresponds to an interface in the temporal direction. Okay, the interface in the temporal direction between a trivial insulator and a chain insulator. Okay, is that right? Okay, because this trace, I mean, so this side is an interface between the chain insulator and the trivial insulator, and this another side is another interface. Okay, and we know very well the interface between chain insulator and the trivial insulator has a chiral edge mode in space, at least. Okay, has a chiral edge mode in space. Okay, so let's imagine we also do a space-time rotation. Okay, this interface becomes a spatial interface. Okay, then we know that actually, I mean, at the interface there should be chiral edge mode. Okay, but we have two interfaces here. Okay, so eventually this actually will become a will be a non-chiral edge mode. Okay, non-chiral edge mode. Okay, so now you can see that this Z, the fidelity, now must become a partition function of the edge mode of the chain insulator. Okay, is that right? Because Z is a path integral. Okay, Z is basically the path integral with a Hamiltonian on the top half and a Hamiltonian of chain insulator on the bottom half with a two interface. Okay, then this path integral must include the path integral or the partition function of the 1+1 dimensional non-chiral Dirac fermat. Okay, 1+1 is non-chiral Dirac fermat. So Z becomes a partition function of CFT. Okay, partition function of CFT. So let me remind you that actually the rho, I mean the chain insulator is a fully gapped system. Okay, and actually the trivial insulator is also a fully gapped system, and there's no spatial boundary at all. Okay, so, I mean, so let's say both systems are defined on periodic boundary condition. Okay, there's no spatial boundary at all. Okay, both of them are fully gapped systems, but nevertheless, when we overlap them, when they are overlapped, okay, this overlap will actually contain the information of a partition function of a conformal field theory, which is a gapless theory, okay, which is a gapless system. Okay, and F will be the free energy of the conformal field theory. Okay, free energy of the conformal field theory, and also if there's a decoherence, okay, if there's a decoherence, the decoherence is mapped to some interaction between the two boundaries. Okay, interaction between the two boundaries. So it means that the decoherence is mapped to the partition function of a non-chiral CFT, but with some interaction between the left moving mode and the right moving mode. Okay, between two of them. Yeah. Okay. Sorry, my battery is running low. I need to plug it in. Yeah, right. So Not sure it works. Yeah, okay. So let's think about some simple scenarios. Okay, so let's say that my chain ruler has a U1 symmetry, of course. Okay, then actually the interaction induced by decoherence depends on the symmetry condition. Okay, suppose I have a one chain insulator, and actually the decoherence channel preserves the U1 symmetry. Okay, preserves the U1 symmetry. Then actually the interaction between the left and right channel preserve the U1 symmetry, then there's no backscattering which can happen. Okay, so it means that under decoherence, with a doubled U1 symmetry, okay, with a doubled U1 symmetry, then this Z will always be a particular function of a gapless CFT. Okay, and F will always be a free energy of a gapless CFT. Okay, because as long as I preserve the left and right or the doubled U1 symmetry, actually, they cannot be gapped out at all. Okay. On the other hand, if I only preserve the diagonal U1 symmetry, okay, if I only preserve the diagonal U1 symmetry, then the Z and F will be gapped. Okay, Z and F will just become a partition function of a gap system. Okay, without any sign of the free energy. Okay, without any sign of free energy. Or actually, more quantitatively, the previous case corresponds to a situation where the central charge equals to 1. The second scenario corresponds to a case where central charge equals to 0. Okay, but now let me discuss a slightly more complicated or slightly more interesting scenario, which means that I have a chain insulator with a chain number equal to 2n. Okay, so this rho C is a density matrix for chain insulator with chain number equals 2n. Okay, and then the 2n, this CFT for the 2n chain insulator. The overlap between the 2n chain insulator and also the triple insulator, it will have a CFT which is the U2n level 1. And this CFT has doubled symmetry U2n left times the U2n right. Okay, has a doubled U2n symmetry. And then actually and the central charge equals 2n. Okay, central charge equals 2n. And then we can actually choose what channel to turn on decoherence on. So for example, U2n obviously contains a SU2 subgroup. Okay, obviously contains a SU2 subgroup. We can choose to weakly measure the SU2 current
We apologize for the technical difficulties. We'll be back in a second when the computer reboots.
And muted. Yeah, okay. Yeah, right. So yeah, anyway, so here I'm trying to say that actually, okay, so maybe I can repeat a little bit from the previous slide. So I'm trying to say that the decoherence act as an interaction between the two the left and right moving modes of the CFT, and actually it can reduce the U2 and level 1 CFT to some CFT without without a integer central charge, because it gaps out the SU2 level n part of the CFT. Okay, so how do we see the CFT? We can define the chain insulator on a cylinder, on a spatial cylinder, and define the trivial insulator also on a cylinder. Okay, and then the free energy defined above, okay, the effective free energy, the log of the fidelity, should have this kind of finite size scaling. Okay, there's a so first of all, the density along the y direction will scale linearly with the circumference of the perimeter of the cylinder, but there's a subleading term which is proportional to the central charge. Okay, proportional to the central charge. So in principle, one should be able to simulate this density matrix in computer. Okay, on a decoherence and check our prediction based on field theory. Okay, and to extract this central charge. Okay, so different decoherence channel with different symmetry can tell you the different. Can tell you the outcome of the decoherence, can change central charge. We should be able to extract central charge from this computation in principle. Okay, and we can also go further. Okay, so previously I said that suppose we calculate the overlap between the two wave functions, two density matrices, or actually we calculate the overlap between two wave functions. It's called fidelity. Okay, but this is another quantity that we kind of played with, proposed like maybe, 10 years ago now. Okay, so this is called a strange correlator. Okay, strange correlator. So basically we calculate the correlation function sandwiched between two wave functions divided by the overlap between the two wave functions. Okay, and this back then, we are very bad at naming things. So this is called a strange correlator back then. But actually, pictorially, okay, this quantity has a nice intuitive understanding. So this omega, okay, can be viewed as evolving the system backwards along the imaginary plane with a trivial insulator, for example, and the psi can be understood as a state evolving with the SPT or a topological order Hamiltonian, okay, along the positive time, and they have the interface at tau equals 0, okay, at tau equals 0. And actually, we can also do a space-time rotation, okay, and then actually this quantity will become the correlation function between an SPT wave function and actually a trivial wave function, an SPT state, a trivial state as a spatial interface. And then this correlation function must be non-trivial, because actually we know very well that actually the spatial interface or the boundary between the SPT state and trivial state must be non-trivial. Okay? Okay, so that means actually, back then we proposed this as a diagnosis for SPT wave function. Okay, we say that if you are given a wave function, okay, through simulation or whatever, if you are given a wave function and you know it's a symmetrical wave function, but you want to know whether it's a SPT state or trivial state, okay, what do? You just take this wave function, calculate the quantity. Okay, if it's an SPT wave function, you are supposed to see power law correlation or long range order, at least for 1D and 2D. Okay, at least for 1D and 2D. Okay, so this was what we proposed a long time ago, but actually we can also, so this was also tested using tested numerically for many SPT state in 1 dimension and 2 dimension. So so basically because we want to study decoherent states, we need to generalize the previous strain correlator into the form which involves the density matrix. So it turns out that this is the form with density matrix. Okay, so basically the previous quantity strain correlator can be written using density matrix like this: the trace, the density matrix 1, and some operator sandwich between them, and the density matrix and second density matrix. And if we calculate the ratio between the top, the numerator, and denominator, which the fidelity, this will give you a strain correlator. But then there's a second version of the strain correlator, which is this. Okay, which is this. So imagine that suppose we take a trace of the two density matrix. Okay, take a trace of the two density matrix. there are two temporal interfaces at tau equals 0 and tau equals beta. Okay, the previous strain correlator corresponding to calculating correlation function at one of the two interfaces. And the second strain correlator corresponds to calculating correlation function for operators sandwiched between at both interfaces. Okay, at both interfaces. So it turns out that we evaluated the both of these kind of generalization of strain correlator. They also can be viewed as generalization of the fidelity I discussed before for many SPD states, and actually we can see many interesting physics emerging when we calculate this kind of quantity. Okay, but for more details, you can refer to this reference. Okay, so that was a lot of field theory and quantum information. So let me summarize. So basically, we try to use field theory to study some class of quantum information problem, and we say that actually the decoherence and weak merriment can be mapped to the problems of boundaries and defect or interaction between defects in the quantum field theory formalism, and we show the examples with quantum critical point and also topological order on the decoherence. Okay, yeah, but there are many generalization and new directions to explore. So for example, so far I have only discussed the boundary of critical point and the boundary of SPD state. Okay, but what if there's a mixed boundary? Okay, so what if I calculate, for example, a overlap or fidelity between a critical state wave function and SPD state wave function? Okay, so both boundary effects should be at play. Okay, there's interplay between them. Okay, this has not been explored so much. Okay, and also so far I only talked about the behavior of Wilson-Fisher fixed point. Okay, under decoherence and weak merriment. So what about phases with fractionation? For example, algebraic spin liquid under decoherence. Okay, this is a new territory. So this was actually explored a little bit in our old paper, but I think there's a lot more to do. Okay, a lot more to do. Okay, because a lot of because nowadays we understand a lot about the fractionalized phases and the fractionalized critical points, and we can try to understand how they behave under weak merriment and decoherence. Okay, so that's the end of my talk. Okay, thank you for your attention. Okay, and sorry about the technical.
Any question or question from the Zoom session? Yeah.
So in this second point that you pointed out about studying this kind of phenomena in spin liquids and fractionalized phases, do you expect or do you observe some kind of robustness against weak decoherence, that you slightly break some kind of symmetry, but you still have this non-creative?
Yeah. So far, yeah. So as I mentioned, we only explored a little bit so far. I mean, but from what we saw so far for a gapless state with fractionalization, but turns out that it's quite fragile to the decoherence. So even for weak decoherence, it's quite fragile actually. So basically the decoherence tends to cause confinement. Yeah, but for gapped topological order, even though the question is for gapped topological order like toric code. So normally we know that when you turn on temperature, there's no toric code, but our calculation shows that under weak decoherence, there's a critical point, below which it is still a topological order. Above which it actually lose some of the quantum decoherence. There's a phase transition between the weak and the strong decoherence channel. Yeah, but still there's a lot more. I mean, I don't think I can make a general statement right now, but yeah, there should be a lot more to explore.
Yeah. And in the protocol, you mentioned that the critical point, the PEC, was not that small. How large is it?
0.2 something, or I forgot. Yeah.
I have a question. So is there a way to measure that set of the type 2 strange correlator, because that involves double?
It's very difficult. Yeah, I have to admit that for type 1 strain correlator, Jiang Yang has some proposal about how to measure it. But for type 2, it's difficult. Yeah, for type 1 strain correlator, it's kind of like mirroring a non-local string operator. But for type 2, it's more involved. It's much more involved. So it's not going to be very easy to measure. But one can also always simulate that. So
Yeah, probably another question. So for a string correlator, it's something like boundaries on the time domain can be rotated to the boundaries on the spatial domains. But when like JB and company introduced some open system or average SPTs with subsystem symmetry, which you have to break Lorentz invariance, and hence their wave functions, even in some fixed point, cannot be mapped to some.
Okay. See, I mean, so the space-time rotation is only needed for your calculation, but actually, no. So even without space-time rotation, we can. I mean, yeah. I mean, well, I think we can prove that actually the string correlator must be non-trivial. It cannot be short range. The reason is that remember so for example, the cohomology classification of the SPT, right? So what they were really classifying is actually the action, the fixed point action in space-time, in the triangularized space-time. So this action should have an anomaly at either temporal boundary or spatial boundary, right? So that means that if you measure correlation function at the temporal boundary, it should still be non-trivial, even though it may not look the same as spatial boundary, but it cannot be trivial. That's the statement. Yeah, so it's just for some system, it's easier to calculate the temporal boundary correlated function when we do space-time rotation. But actually, even if we don't do that, it should still be non-trivial.
I see. And also for versus whether you have local decoherence quantum channels versus in the Hamiltonian level, like average SP, you have disorder field and disorder average. Is there really a difference between these two in terms of SPT? Because what we are really looking at is just looking at the anomaly on quantity.
Well, I think they can still be.
Or is there anything which can be?
See, I mean, so here actually, yeah, it's really a question of how to define non-trivial SPT. I think we need a proper definition for a general definition for what. So what do we mean by a non-trivial symmetry protected topological ensemble? So this actually, yeah, right. So we don't have a very good definition yet. And actually for average SPT caused by disorder, we can just use the old definition, just look at physical boundary. But here may not be the case because actually it's a more non-trivial mixed density matrix now. Yeah. So so we need a proper definition for the symmetry project topological ensemble in general. Yeah, before we can answer the real difference or not.
Other question?
Yes, this one. So if I remember correctly, like the measure of the code is always like the phase transition is like the 2D IC type. Do you think making some?
It's not always like that. It's like for
let's say, is it possible? Let's say design other types of meshes, you can realize other regularity.
Yes, right. So we only started the second range entropy, but actually the Berkeley group started any range entropy. Actually, sorry, any index n, and actually only for the second range entropy the problem is mapped to the exactly mapped to the 2D IC. For other range entropy n is mapped to some other model, some other universality class. Actually. Yeah, some Potts model, and if it's n equals 1, it maps to the Nishimori line of the random bound IC model. So the model actually you get actually depends on what actually what random index you're looking at. I think there's another question I just saw on the Zoom. No, okay.
Hi, Cenke.
Oh, yeah.
Can you hear me now? Hello?
Yeah, Noah was saying.
Cenke. Can you hear me now?
Can you ask out loud? Mute yourself.
Can you hear me now?
Yeah.
Hello? Oh, hey, hello. So hey, Cenke. The question is goes back to Lee Dong-Hai's many body course, many years ago. I guess we were alive then. He notes there's a famous theorem due to this guy named Marshall that applies to symmetric Hamiltonians. It was raised in the introduction to your talk when you mentioned this symmetric Hamiltonian And it's, you know, it's interacting with environment. And somehow for solids, we have this feeling that everything happens very fast. But in a simulator, maybe we can investigate the question that's posed by this Marshall theorem, say for the Heisenberg model on some simple lattice, bipartite lattice, something you can do Monte Carlo on, you know, like a chain or a square lattice, antiferromagnet, say spin 1/2. The theorem says the ground state is unique and symmetric, just like the the Hamiltonian. But then we do neutron scattering and we find Nail order, we find some kind of breaking of the symmetry. This distinction between the ground state that you find for exact Hamiltonian on lattice and the long range order that we observe in solids and so on, it has to emerge in a simulator at some point. You know, when you have, say, 10 to the 23 atoms, it'll happen infinitesimally quickly. But let's say you have 1,000, and I wonder if you thought about how we might approach this old problem. You know, how does symmetry break? How does matter condense? How does a system go from being the eigenstate of some symmetric Hamiltonian to being long-range ordered?
I think we kind of know that, right? Because actually, we know that if I simulate a spin 1/2 model antiferromagnet on the square lattice, it's always going to be a singlet for finite system size. But let's suppose I marry the spin correlation function, it's going to be long-ranged. So basically, in a finite size system, basically the definition for the spontaneous symmetry breaking should be just a long-range correlation, rather than seeing a non-zero average value of an order parameter. So that's a definition. I mean that should be a working definition for a finite size system, right? Because for finite size system, actually we can pretty much prove that the average value for any order parameter should be 0. So basically, the definition should be long-range correlation.
So how big a system do you have to make before it stops being finite size?
So maybe your question is about whether we can really see long-range order in quantum simulator.
You take some lanthanum cuprate. It's a quantum simulator. It's simulating itself. How does it know to stop being finite size and to start being itself, to start being a magnet? It's some kind of weak measurement.
I don't think this question is relevant to the talk. I don't know.
Well, in terms of
here, so what
right? What
are you trying to say?
So the question is, if we think about the system as kind of going through some kind of weak measurement, maybe we can understand the way that it goes from being just some finite system that Adrian can simulate to being something that, you know, has a long-range order in the sense of, you know, staggered magnetization. But I didn't, like Adrian points out, I didn't hear it in your talk how we might approach that problem. It seems like a different problem than the ones that we're able to solve so far. But is that maybe not true? Can we already solve it using the existing method?
Yeah, I didn't quite hear. No. But we can well no you have my email. We can discuss over email. Yeah.
Okay. Thank you, Adrian.